Okay. And also, last week we saw how to solve sometimes or reduce to the minimum those issues related to this aliasing. We completely solved the problem and the leakage. Now, we are going to see what we can do if, for example, while we are doing our tests in the laboratory, we figure out that our chosen frequency range is not the good, and specifically we would like to have some information, more detailed information in a, let's say, different frequency range with respect to the initial one. That's because maybe you were wrong in deciding the frequency range, or something happened that that requires additional analysis, detailed analysis. The main purpose of that could be, the main issues of that could be solved just by retaking the test. So we start from scratch, all the acquisition parameters in terms of sampling points, frequency range, and check the new windowing functions and so on. Sometimes that is not possible to carry it out because you already have everything in place, or even you are practically packing back all the things together, and therefore all the tests could not be run once again. So what we can do is to apply what is called the zooming technique. And actually, this zooming technique is a shift of your signal in the frequency domain so that you can have all the available sample lines, frequency lines available as your resource, all available there in the new frequency range. So the zooming technique is a technique, of course, that shifts in frequency domain your uh, information that is in your recorded signal, okay, so that a higher number of frequency line is available in the new frequency range. Okay, and that's the reason why it is called a zooming. That is, we are shifting all the information, uh, all the resources, digital signal processing resources, from the very beginning, that is for the whole frequency range, into a new frequency range. Why that? Because we realize, as I said before, that something went wrong, that we are more curious because something happened in a specific frequency range that is a little bit different than what is expected at the very beginning, and therefore that with respect to the old acquisition parameters that were set at the start of your analysis. How can we describe this zooming technique? Let's assume that we are having a signal, whatever signal, very easy. This signal is in time domain, okay? It is a sinusoidal wave, okay, harmonic wave with an amplitude A and a, let's say, a frequency omega. Okay, now let's introduce one more signal. Let me call that X star, time domain again. Okay, that is equal to, let's say, an amplitude 1 times cosine a different frequency, omega 1. Now, what we can do is take the multiplication between what we already measured, what we got, the initial, the reference one, and this X star signal. And let's call that as XZ, the zoom signal. That is equal to X time times your X star. And that is equal to A sine omega t times cosine omega 1 t. Now, if you play a little bit with the trigonometric formulas, you can easily show that this equation is equal to a half times sine omega negative omega 1 t plus sine omega plus omega 1 t. Okay, and that is the trick. If you see now what we got, we end up with a harmonic signal once again, but it is having two different harmonics. So we end up with a new signal with two harmonics. The first one is omega negative omega 1, and the second one is omega plus omega 2. And that's it. Now, what we are having is just we shift your information from the original frequency, omega, to two different frequencies if you want. The first one is omega lower 1, omega negative 1, omega 1, and the higher one, omega plus omega 2. So your whatever center frequencies has been shifted by these values. Okay.
Excuse me, Professor. It shouldn't be omega plus omega 1.
Yes, omega negative omega 1. Oh, sorry. Yeah, sure. Omega 1. Okay. Now, if we, for example, remove one component in this new signal just by using a low pass filter or high pass filter center with this new frequency, then we have a different signal that is just shift. Okay. So if one component is removed with let's say low or high pass filter, okay, then what we got is your new signal, that is your zoom signal, is equal to a half sine omega plus minus omega 1 t according to the different type of filtering. Okay, so what we got then, what we got is that we shift the original signal okay around the new frequency omega star, that could be equal to omega plus omega 1 or omega negative omega 1 according to the different pass filter that you use. low or high pass filter. Okay, and thus, therefore, it is possible to use all the available frequency lines, okay, for further signal analysis. Okay, so what we did is just this zooming technique. Yeah, this zooming technique is just a way of shifting, as I said before, your frequency content from the original center frequency, if you want, to a new one that we call omega star. Okay, and we can do that just by introducing cosinusoidal signal, okay, that is multiplying your measure one, and then just apply your pass filter, low or high pass filter, so that to select, to choose, or to remove the higher or lower frequency according to what is your need. Once again, there is not a need to resample, redo everything from the very beginning. You can do that at your home, in your office, okay, just by considering your measures quantity and then apply this technique. The main advantage is that you can have a refined vision of what are the signal properties in the neighbor around your new frequency omega star, because you can use all your frequency lines just in that new with that new center frequency. Okay. um another another technique that I would like to discuss with you very briefly is the average. Okay, so averaging. This averaging is very useful, averaging of the signal. Okay, so your signal averaging is very useful, okay, to remove noise from your measurement, okay, through, and that is done uh, by taking averages of your recorded signal. In a in a in a way, it is just as fictitiously introduce new testing. A sketch that could help you in understanding what is this averaging approach to your signal. Let me consider that you are having, for example, whatever response is. Let me pick one among all the possible over xt. Okay, and this is your whatever response. Okay, and this whatever response is recorded, okay, with this observation time. Okay, well, we have done that. We are very happy about that. Once we are at home, maybe we can think to even increase the noise reduction from your measurements by introducing, let's say, a number of data block. Let me say this one. Okay, data block 1, data block 2, 3, 4, and so on. Okay, so one block 1, another block 2, 3, and so on, in this case 4, and then average all these data blocks together. Okay, so that what you're having is the average signal is the same time domain, of course. Okay, but that is an average, and the length this time is just the observation time divided the number of blocks that you are considering. And so you are averaging everything here. Okay, we are having a, let me call that average process. Okay, so if you want, it is just taking the average of the ensemble, but now the ensemble is a subset of the overall sampling times that you are having in the whole period, observation period T, capital T. Okay, a slight different procedure that that is capable to improve even more the noise reduction is to use what we call the overlap. So once again, let me show you what is done with the overlap. Okay, this is the time, this is your whatever response, that is typical response, whatever. So the overlap is your observation time is still there. So the overlap is to consider number of blocks, for example, this one. Okay. Then the other one is overlap with the other one. So the size of this block is the same as before, but now what we are having here is an overlap. Okay, and therefore we got is introducing additional overlaps. Okay, so overlap there. The overlap is expressed in terms of percentage of the overall signal. So if you have an overlap of 100%, that means that you're using the same information that is containing just one overlap, so it is meaningful, of course. So generally what we are having is 10, 20, 30% of overlap. What is the main advantage of that is that we are increasing even more the number of data that we are averaging, so that there is a chance of reducing once again the noise, the effect of the noise in our measurements. What is the cost that we have to pay in doing this averaging? The cost is that we are no more having the whole capital T in terms of measurements. Okay, the observation period that was equal to capital T is not more there, because we reduce fictitiously the observation time to what we call here T over number of blocks. Okay, so that's the reason why that it could be reviewed this as the cost we are paying in reducing the noise. So the higher is the number of blocks, the better is the noise removal, but the worst will be the frequency resolution, because the fictitious observation period will be reduced. Okay, and that's the reason why we can have some overlaps. Okay, and these overlaps can improve your noise reduction, but however we can't go so far because we can't have an overlap of 100%. That means that we are having just one block that we are considering for all the time, so no averaging at all, actually. Okay, so it is once again a matter of balancing between the need of noise reduction, but however the requirements of a good accuracy in your digital analysis. Okay, so now let's see what happens about the other point that we discussed at the very beginning, of this topic. Remember, we talk about discretization, and we were mainly referring to the x-axis. Now, what I would like to stress a little bit with you is what happens to the quantization. Okay, that is, we are once again living in a digital world. Okay, and because of that, not only we have to consider that your signal is defined in a discrete numbers of time samples, okay, but also its values, its value, that is the y values, is not a continuous function, but it is defined over a number of quanta levels. Okay, so this is introducing the dynamic range concept. Okay, and this dynamic range is referred to the fact that each sample quantity is quantized. What does it mean then? Let me say that we are having your analog signal. Okay, that is the one that is coming from your accelerometer, from your strain gauge, whatever. Then what we have to do is apply your anti-aliasing filter. Then what you have to do is to apply your windowing function to reduce leakage. Okay, and finally you can have a sampling of that, of your data, and I've just write that your sampling time delta t is equal to 1 over your sampling frequency fs. And once you're done with that, finally what you have to do is to consider your data quantization. That is, how is the value of your measured quantity? We're referring to quanta levels, we're referring to the digital world. Okay, so the dynamic range in this framework, the dynamic range, okay, is the ratio, is defined as the ratio between the largest and the smallest measurable one variable. Okay, of the amplitude of the signal. Okay, so your dynamic range, let me call it dr, dynamic range, is by definition the ratio of the maximum measurable value of the amplitude of the signal, okay, divided by the minimum of the measurable value of the amplitude of the signal. Okay. If you are referring, for example, to a sinusoidal wave or whatever harmonic signal, could be defined as the ratio between the largest sine wave RMS root mean square value with respect to the RMS value of the noise. Okay. Now, when referring to your acquisition system, then we have to refer to the electrical parameters, electrical quantities that are characterizing your measured quantity. And generally, what we are referring to is to, for example, the current or the voltage. So whatever is the intensity of your measured quantity in the acquisition system. So that definition could be also referred to, so referring to your acquisition system, that dynamic range could be viewed as the maximum value of your amplitude of the measured quantity divided by the minimum quantity, measurable quantity. Okay, and that is generally expressed in dB scale. dB scale, that could be very large variation. Okay, so what we are having is that the dynamic range, so dynamic range is defined as 20 logarithm base 10 of the ratio max, amplitude max with respect to the amplitude B. Okay. Now let's point out some items that are of interest for this analysis. In a general AD converter, ADC, analog to digital converter, okay, the minimum value depends on the accuracy, okay, of the measure. Such an accuracy, so item, is given by the number of quanta levels. Okay, that are just referred to bits, okay, that are used by your ADC converter. Okay. Generally, this ADC uses 16-bit or 24-bit quanta levels. Okay. That is currently ADC uses 16 bits or 24 bits. Okay. as quanta level. That is, just to give you an idea, that is the number of quanta levels is 2 to 16, that is 65, 536 levels, or 2 to 24. Do that by yourself, the number of levels that are. Just to explain that, if you are having your whatever measured quantity, okay, your time, and that is your whatever measured quantity that has, for example, a very nice behavior as the one that I've just drawn, then we have to consider that not only we are having time discretization, and we already talked about that, okay? So that is your time discretization. But also your value here, the y-axis value, is defined better on a number of quanta level. Okay, so you are having, for example, at that line, we are having a number of quanta levels like this. So this value will be in between one quanta level or another one, and this number is equal to 2 to the number of bits. Okay, let me say that as n bit. Okay, and that is what I call the discretization in the y-axis. Okay, now let me see now what happens concerning the evaluation of the minimum value, that is your accuracy. Okay, so the minimum measurable value depends on the measuring range, of course, and on the quanta levels. Okay, so your minimum quantity, amplitude of the minimum quantity, okay, I mean, is your range, okay, that is your measuring range, over this number of bits. If you want, that is equal to your Emax, Imax, the I minimum divided by the number of bits. Okay, and this number of bits, as we already discussed, could be equal to 16, 24, that are typical numbers for the actual AD converter. That is, once again, this minimum value is telling me what is the accuracy, okay, of your measurement. Now, let's focus on the maximum value, okay? So the maximum value is given by the maximum measurable amplitude. Okay, and therefore we can say that the maximum value is just the measuring range. Okay, and thus having that in mind, once again, you're measuring range. So having that in mind, we can define that this dynamic range is defined by 20 logarithmic base 10 of that ratio, the maximum divided by the minimum. Okay, and that is equal to 6.02 number of bits. Okay, number of bits value, and that is given in a dB scale. Okay, now just to put some numbers, if, as an example, of course, if your AD converter is characterized by an bit equal to 16, then your dynamic range is equal to about 96 dBs. If your number of bits that is characterizing your ADC is 24, then your dynamic range is equal to about 144 dBs. And that is telling you a very important aspect of your acquisition system, that is how precise could be the measurement of your whatever varying quantity. Okay. Now, just to
nella definizione di in minimo, ma al denominatore non abbiamo quindi 2 alla n bit?
sì.
Ah, ok, però c'è scritto.
No, ho sbagliato. Giusto, sì, 2 all'NB.
Grazie.
Ho sbagliato a scriverlo. Aspetta, lo cambio. Certo, grazie. I was wrong in writing this. Okay, is 2 to n bit, 2 to n bit. Okay, thank you. Okay. So, if you are now evaluating what is the tension that you have to, for example, consider in this discretization, in this dynamic range, no? Let's assume that if now the measuring tension rise in a typical voltage range of plus minus 10 volts, okay, and that is typical range. Okay, then your minimum quantity is your delta V over 2 to the number of bits, okay, and it is equal, for example, 20 volts divided by 16 if you are considering your number of bits, so your AD converter equal to 16, and that is equal to 0.3 millivolts. Okay, and of course the dynamic range is very easy, it's not dependent on this voltage. Okay, so it's 20 logarithm is 10 once again of 20 volts divided by 20 volts over 2 to 16, and that is equal practically 96 dBs. Okay, so this very easy example is telling you what is the minimum quantity that we can associate to a specific quanta level, that is 0.3 millivolts in that case. Okay, and of course the dynamic range is a total is 96 dB. Of course, we are assuming that your AD is characterized by 16 as the number of bits that we are using. Do you have any questions on that? Okay, if there are no questions, I would like now to move to the topic of this course, that is the testing from the dynamic point of view or whatever dynamical system. Okay, while doing that,
Excuse me, Professor.
yes, question.
Okay, in the DR, the formula is 20 logarithm of delta I over
Yes,
2 times NB.
the maximum, okay, is 20 volts. I can
Mhm.
rewrite that maybe divided by the minimum. Okay, so 20 volts divided by the midvolt, that is 20 volts over 2 to 16, if 16 is the number of bits that your AD converter is using.
Okay, thank you.
Now, as I said before, let's consider typical dynamic investigation, and therefore we enter the core of this course. Okay, and in order to do that, let me ask you a question. Why we are taking dynamic testing? Why we do require to dynamic test your whatever structure? Do you have a clue about that?
To see what will happen to the structure in a time, not
In time and frequency, better, yes. But why we would like to see what happened? Remember that when we are going down the laboratory, we are starting spending a lot of money. Okay, if you think that you have whatever aircraft, whatever satellites stopping in the hangar in the laboratory for testing, that means that it's not producing anything. So just because this system is still is stopping there, we are losing money. Then you have to add time to test it. So you have to pay the engineers there, people, workers, whatever, and pay a lot of money for transducers, system acquisitions, and whatever. So there is a lot of time and cost associated to testing. So why do we need to do that? We already asked to this question when we were dealing with static tests. So what is the purpose? It's a question for you, huh? I'd like you to respond to this question.
Okay, the thing that I remember is that we want to see when we will go through the plastic condition,
Okay, so
or
it's not really that, but the issue now is that we would like to assess, to validate your general dynamic model of your whatever system. Okay, so we would like to, for example, to assess that from the finite element analysis. We got, for example, your mass matrix, your K matrix, okay? Then the experimental testing, experimental dynamic, of course. Will assess the correctness of the numerical predictions. That is the mass and it is your mass and stiffness matrix. Okay, and that is done in a specific domain that is done in the modal domain. Okay. Is general, is not always said so, but generally is done in the modal domain. Okay, so from numerical analysis, we can have mass and the stiffness matrices, or that is the same, your response model, that is your frequency response function, or once again, we can have your poles and eigenvectors, so matrix. Okay, so here are mass stiffness matrices. Here is the frequency response function. And here are the poles, that is natural frequencies and damping ratios, and modes, corresponding modes to the nth natural frequency and damping ratio. Okay. From the, on the contrary, from the experimental investigation, what we are generally having just the poles and the modes, no more than that. Thus, the comparison and then the assessment is carried out by us, carried out in the modal domain. Okay, in general, let me find that in general. Okay, so the question, why we need to test the structure from the dynamical point of view? The need is because we would like to assess that our finite element model, for example, is representative of our actual dynamic behavior. Once you got this, once you have your finite element model validated, then once again, you are a rich man. You got the power in your hands, because you can not only predict what could be whatever system response according to the different input loading excitation, but also what we can say is that we can also predict what is a possible effect of structural modification. Okay, and therefore we are very interested in assessing your numerical model using your tests, using the experiments. Of course, because as I said before, those experiments are very costly and lots of time demanding. We have to plan well in advance all those tests in order not to let's say forget some specific points, some specific behavior, but on the same time, we are not over testing the structure in order to reduce time and not spending that much. I would like to share with you a general step analysis of what we can have. Okay, just one sec. All right. Okay, please. Yes. I'm sorry, but it is 90-degree rotated, but I think that you can read it as well. So we can start from the very beginning, or that is could be either existing or just a design drawing or data. And then what we are doing is just try using the equations that you know very well from your last year course in aerospace structures, then try to represent using an analytical model what could be as a representation the behavior of that structure, for example, under both static and dynamic point of view. Once we got those analytical model, let's say this structure is behaving as an Euler Bernoulli beam or as a 2D plate, for example, thin plate, and so on, then we derive the mathematical model that are our differential equations that we want to have, and then we can predict as a solution of those differential equations the dynamic behavior. Okay. And that is all belonging to what I call what Lewis is calling actually the analysis step of your design. Then the question is, are we in need of doing some tests? Okay. If the answer to this question is no, what we have to do is just verify that there are some design changes that are required. If not, we are very happy about that. If some design changes are required, then we have to go back to your analysis and redesigning the structure. So we have to see what are the changes that we are in need. So if there are some design changes, we have to include that. And it could be done also by verifying or reassessing the assumptions that are referring to the analytical model, or by refining the mathematical model that could give you the answer to your question. And then we start the loop once again. Once we are having the structure, okay, and then the analysis is done, then we have to, and if we have to answer to the test question yes, then of course we have to first introduce your physical model, so your mock-up, your whatever made a structure, we need to have it, okay, if not, and then go through dynamical testing. And this, if that dynamical testing is telling you that those predictions, those estimates in terms of model parameters, as I said before, are the same as those predicted by your numeric analysis, then you are very happy. Then you can start having a party for the whole weekend, and then lock in your safe box all these models because they are representing for your farm a very powerful arm in order to sell a very sound and good design. Okay, I'll give you the PDF of this block diagram just to for your own properties. Okay, so now let's have a break for 5 minutes. So we will resume the class 3:15. Okay. If there are any questions, meanwhile, I'm here.
Professor, there is a question in the chat.
Is there a question?
There's a question in the chat.
Okay. The question on the chat is referring to the effect of the air surrounding your structure in your dynamic testing. That could be important effect, but that depends on the scale of your experimental investigation, that is on the frequency of investigation. For very low frequency, maybe those effects are negligible. For higher frequency, maybe those effects I have to be considered. Also depends on the density, for example. And so it's a sort of dimensionless numbers that we have to consider, let's say Reynolds, Freud, so that we can have an idea of what is the major effect that we have to consider in our analysis. For your information, when you are taking what we call the ground vibration test, that is your experimental mode analysis for whatever vehicle, then the effect of the fluid, of the air surrounding the structure is visible. On the contrary, when you are having the flight test, then the flight test, it is very important to take into account the airflow, and actually we have a whole aeroelastic effect that we have to consider, and thus for that case we are very interested in the overall couplings between the structure elasticity, the structure inertia, and the aerodynamic flow around the structure.
Scusi, professore, ma
Sì,
per quanto riguarda la prima esperienza di laboratorio,
sto chiudendo la registrazione del video che vi darò nel giro di pochissimi giorni, quindi un po'
ok.
di pazienza.
E volevo,
Dica.
no, sì, volevo chiedere, ma è necessario mandare una mail per dire che si vuole ricevere il video oppure lo condividerà a tutti?
No, lo condividerò a tutti quanti.
Ok, perfetto.
Bene, poi
Grazie
dopo
mille.
su questo punto, ok?
Professore, scusi,
Sì?
mi era stato un attimo, ma di che video parlava il collega? Cosa aveva detto?
Lo so, quali collega?
No, ha parlato del video che lei doveva condividere.
Sì, sì, ma più là, parliamo dell'esercitazione.
Ah, l'eccezione, ah, ok,
Ok,
grazie.
prego. Okay, let's resume our class. Now let's go into some details of our dynamic investigation. In order to do that, I would like to introduce what are the main hypotheses that we are considering when doing our experimental dynamic investigation. Okay, so the main hypotheses that we have to consider are, first, the structure is linearly behaving. The second hypothesis is that the structure is time invariant. Third hypothesis, the reciprocity principle from Betti is true. Okay. Okay. And four, the structure is observable. Okay. What does it mean that? It means that hypothesis number one is telling me that there are no other behaviors with the standard structural dynamics investigation. Okay. Of course, we can also consider other specific dynamic investigations that are referred to non-linear behavior, but that is not our task. That is not our point for our course. Okay, we can have a lot of non-linear analysis from the structural dynamic point of view, but now we are focusing on just the linear analysis. The structure is time invariant. That is, we are not considering all the cases that are referring to, for example, a mass change or a stiffness change. So if you would like to experimental investigate an aircraft that is flying from here to New York City, for example, then we can't have just one test, because when the aircraft is moving from here to New York City, then there is a very great change of the mass, and therefore the hypothesis of time invariant system is no more satisfied. In order to do that analysis, of course, we have to consider different parts of the flight missions, and then we can have assume that for each part of the flight mission, the system is time invariant. The same discussion could be done also when referring to space rockets, of course. Space rockets, as you very well know, in let's say 1 to minutes time, loses practically all its mass, 70-80% of the mass, even more. Okay, and therefore we are not considering that structure for the whole mission time. But what we are considering is a piece wave analysis, of the different parts that are composing the mission, and for each part I am assuming that the system is characterized with constant mass and stiffness. The Betti's reciprocal principle is telling me that you can have that your stiffness matrix is a symmetrical one. Okay, I know that you are all aware about Betti's reciprocity principle, but just me remark you that it is the principle that is telling you that if you are loading the structure in a point and you measuring the deflection of that structure in a different point, that deflection is the same as you could have when exciting the structure with the same load as before, but in the output point, and considering the output measure as the point, as the one at the input measuring point. Okay, and that is equal to say that K, the element Ij of the stiffness matrix, is equal to the element Ji of the stiffness matrix, or the stiffness matrix image. And the structure is observable. The structure is observable. It means simply that the measured quantity, the input and the output, allow us to perfectly identify the system. Okay, so let me write this one because sometimes it's not very well considered this last point.
Excuse me, Professor. I have some
Let
interruption when you're speaking.
let
I
me
don't know if it is in.
let me write
Okay,
this one please first. Okay,
thank you.
so the measured quantities. Okay, that is input and the output. Okay, to allow to identify the system properties. Okay, question? Any question? No question anymore? Okay. If there are no questions, let me keep going. So these are the main hypotheses that we have to consider. For hypotheses that are very nice, but we have always to remember that, because if you are missing some hypotheses, if you are not aware that you are, let's say, against one of these hypotheses, maybe you can have some results that have to be considered as bad results, not a good. And remember, last week we referred to the GIGO analysis. This is garbage in and garbage out analysis. So please remember this hypothesis in order to be sure that all your analysis is consistent with all your analysis tools. Okay. So what are the main steps? What are the main subjects, if you want, that you need to have a good command when taking this dynamic testing or the experimental model testing specific? Okay, so the experimental model analysis, we refer to that EMA, okay, is based on these items. So the first one is the analysis theory. Okay, and I know that you are masters in modal analysis theory. Then the second item that we have to consider is the experimental modal analysis methods. And we are going to enter these methods. Okay. The third item that you must command is the modal data acquisition. And with the brief review of the digital signal processing that we had so far, and with some additional details that we are going to consider during our laboratory activities and some other theoretical part, you for sure will have a good command on this third step, third item, that is modal data acquisition. Then the fourth important item that you have to know very well is the modal parameter estimation. Okay, and also for this part we are going to enter some details in a few classes from now. And the last part, that is very easy but we have to consider, is the modal data presentation and of course validation. We will focus on this last item, that is modal data validation, because we already know how to show your data in terms of plots, in terms of animations and whatever, that are very, very easy to do. Okay, now let me, if there are no questions, let me start your analysis of your experimental of the experimental estimation of your frequency response function. Okay, your frequency response function is, let's say, something in under the hypothesis that I just remarked before. Okay, that is just telling me what are the properties of your structure. Okay, so in this box what we are having is your structure that is characterized by your impulse response function in time domain. What is doing my impulse response function is just relating my whatever input, okay, for example input excitation or input force, and your whatever output that could be your acceleration, your displacement in the time domain. Okay, or on the other side, in the frequency domain, we are having that your system, okay, is characterized by a frequency response function that is representative of behavior of your system. We are having your impulse excitation, your loading excitation in the frequency domain, capital F, and you are having your output response, that is your capital X, in the frequency domain. Okay, these two divisions are the same, that these are telling me what are the properties of your system, one in the time domain, the other one in the frequency domain. You know, I know that you know very well all these properties, the age properties, just to remark, the age, the frequency response function or the impulse response function are not dependent on both the input and the output. They are just the intrinsic properties of the system. But what you are doing is just sort of evaluate and therefore estimate from the experimental point of view those properties, the age, just by the measuring of both the. Now, in the time domain, just to be sure that we are talking the same language, in the time domain, in order to have your output response xt, we have just to make the convolution of your whatever input and your whatever function that is representative of your system. So you have to take this ft, that is the convolution with the impulse response function. Okay, this is the convolution, or the integral, if you remember well. Now, if we take the square okay of the previous equation of everything, and we make the Fourier transform. Okay, what we got is the information of the power spectral density. That is the relation between the power spectral densities of the input with respect to the power spectral densities of the output. So what we can say is the SXX, that is the auto power spectral density of the output, that is equal to the auto power spectral density of the input times the amplitude of your frequency response function square. Okay, just to remember, that is the auto power spectral density of the output, that is the auto power spectral density of the input, and of course that is the square of the amplitude of the frequency response function. Okay, now let's go back one line or two. Yes, let's assume that we are in the laboratory, then we are exciting the structure, and then we are measuring what is the F, both in time or in the frequency domain, doesn't matter. And we also measuring the output responses, that is your X, your output, whatever it be, displacement, velocity, acceleration, doesn't matter right now. And therefore we are having the information both time and the frequency domain of your output. Okay, so I'm asking you, can we use those information to estimate your frequency response function H? Do you have a clue?
I think yes, we can use them.
How?
So we can find a model for them.
No, you are down in the laboratory. What you got is what you have on the screen. What I'm writing, just written.
Can you explain the situation a bit more?
Situation, you are having your system characterized by the H. You are exciting that system with input force F, and then you are measuring the output of that system because of the input force X. The question is, can we measure or can we estimate better your frequency response function and therefore your system? Do you have a clue? A way of doing that is just using this last equation, as you can see. Okay, because if that is true, what we are having is that the amplitude, right, so the amplitude square of your FRF, okay, could be written as the ratio of the auto power spectral density of the output divided by the auto power spectral density of your input. Okay, And that is very easy to do. Now, let me call this way, this estimate, if you want, as the estimate A. Then we will change the name, but just let's consider this as the case A. Let's consider another case, starting from the same equation as before, okay? But let's take the convolution, yes? I don't know. Is this a common problem?
Yes, Professor.
Giorno.
Yes, professor.
Non si aggiorna?
No.
Ok. Can you see it now?
Sì, professore.
Okay. So, let's consider this second case, the B case, and take the convolution, okay, of both sides
Yeah, Professor, can you just scroll it up and explain again because screen was not updated.
I'm just restarting everything. Okay, so let me going back to this equation. Okay, let me call that equation 1. So equation 1. Now, second case, we take the convolution of both sides of equation 1. Okay, this time by your input excitation. Okay, so what we have to do is just consider ft that is convolute with your x, and that is equal ft then convolution with the same ft that is convoluted with the h of t, and then by Fourier transforming once again what we are having is that your f(x) of omega is equal to sff of omega times your h of omega. That is the cross power spectral density between the output and the input is given you by the multiplication, the frequency domain of the auto power spectral density of the input times the frequency response function. And therefore, I ask once again the previous equation. Can we estimate the frequency response function or the system properties just by using the measurements of the output and input of your system? The answer is just there, okay? And therefore we can say that just by using that equation that your h omega is equal to sfx omega divided by sff of omega, okay? Let me now consider case C, a third one. And therefore, by convoluting the previous, both sides of the previous equation, this time by your output response, xt, what we are having is that xt that is convoluted by xt is equal to xt convoluted by ft, sorry, and in time also convoluted by your frequency of function. And then once again by Fourier transforming what we got is your h of omega. Oh, better, maybe before h, let me go straight. That is your sxx of omega is equal to sxf of omega times your frequency response function. Okay, so that is the relation between the auto power spectral density of the output with the cross power spectral density of the output and the input times your frequency response function. And therefore, the same question as before, can you estimate the system properties from the measurement of both the input and the output? The answer is yes, because we can say that your h of omega is the ratio between the auto power spectral density of your output with respect to the cross power spectral density of your power input and output. Okay. So what we got at the very end H, it is the system properties could be estimated. Okay. By three methods. Okay. So the first one is H amplitude square. That is the ratio between the output and the input of f. Okay. Or H, and let me denote this H as H1 of omega, is the ratio between the cross power spectral density of the input and the output divided by the auto power spectral density of the output, or the input, sorry. And H2, let me use the subscript 2 for this last estimate, that is equal to the ratio between the auto power spectral density of the output with respect to the cross power spectral density of the output and the input. Okay. As you can see, we can estimate the properties of your system just by using these three equations. Okay. All these three equations are referring to the input and the output measurements through the information of the power spectral densities. And we know how to obtain that just by considering the signal using the Wiener-Khinchin theorem, and therefore, instead of considering the expected or the expectation operator, that is the ensemble averaging, we are going to the time averaging if the system is excited by a stochastic energodic system. Okay, then we are able, by Fourier transforming this correlation function into this power spectral density, just by taking the estimates using these three equations, we can have the information of the frequency response function. By the way, this is called H1 estimator, and the last one is called H2 estimator. So as a general discussion of these three formulas, what we can say is that in principle, all these three formulas are giving me the same estimate of the frequency response functions. Okay, so from the analytical point of view, we are not having any differences at all. But the first estimate is just telling me what is the amplitude of the frequency response function. We are completely missing all the information concerning the phase of the frequency response function. Remember, the frequency response function is a complex function of a real variable. Okay, the real variable is the Fourier domain variable, the omega, whereas the complex value is telling me that the frequency response function is having both a real and imaginary part or a different representation, the amplitude and the phase. Okay, with the first equation, what we are having is we have an amplitude square of the frequency response function by taking that ratio. But however, we are completely missing by using that the information concerning the phase. Okay. Here we can say no phase information. Okay, so this estimate using the ratio between the auto power spectral density of the output and the input are missing one important part, that is the phase information. So you can't have the whole frequency response function, but just the amplitude of it. On the other side, what we are having is that the H1 and H2, the H1 estimator, H2 estimator, are giving me the full information on the frequency response function. That is the frequency response function as a complex function. And that is true because remember, if we are considering the auto power spectral densities, these auto power spectral densities are real, okay, but the cross power spectral density could be whatever. And indeed, that is the reason why the H1 and the H2 estimator are in general complex quantity depending on what are the nature of the FX, SFX or SXF. So the H1 and H2 estimator are the estimators that are generally used to estimate from the experimental point of view your frequency response function. Once again, we are measuring the input F are under the hypothesis of the fact that the system is linear, is fully observable, is time dependent, is Betti's theorem is there. Okay, so we don't have any other issues. And because of that, we can estimate your response model, that is your frequency response function in the frequency domain, just by taking those ratios. They are not that difficult to obtain. They are very easy to obtain indeed. Okay. The majority of the differences with the, of H1 estimator with respect to the H2 estimators are coming out when you are referring to the noise. Now let's see what happens when we are having noise affecting the measuring chain. So what if noise is affecting the measuring chain? So let's start the analysis. Maybe we will end our analysis tomorrow. But however, let's start our analysis. So let's consider if we are having the output noise. Okay. So first case, output noise. What does it mean? That it means that we are having noise, and the noise is most important at the output stage compared with the noise that is affecting the input. So our is a little bit modified with this. So we are having the same box that is representing your system, characterized by your impulses of function or frequencies of function. Then we are having the input excitation, okay, and we are having the output response like this. Now, what is happening is that because we are having noise, okay, we have to introduce the noise here, okay. Maybe I can be with different colors, okay. Okay, and let me call this noise N, and the result is that your measure output response xm, okay, is the one that is also including your noise, okay. So what we can say is that if we are applying the definition of the H1 estimator, okay, so let me have H1 estimator. If you go back to your notes, you can see that this H1 estimator is given you by the ratio between the cross power spectral density of your H1, yes, of your SFX of omega divided by your SFF of omega. Okay, but now the Fx of omega is have to take into account the measurement quantity. So let me introduce this M that is referring to the measured one. The measured one is, of course, take into account the noise. And so what we can say is that because the summation sign could be considered in your linear transformation from time to frequency domain, what I can say is that your SFXM is given by SFX of frequency plus the SF of noise, okay, of frequency divided by your SFF, okay, the output spectral density, okay. Yeah. Now, what happens there if, and that is always true, if noise, okay, is uncorrelated okay with your output quantity, and that is true, noise is not correlated at all with any quantities actually, what happens, okay, is that your SFN, that is the cross power spectral density of the noise and the input excitation, could be viewed as a zero quantity, because remember, the power spectral density comes from the cross correlation function Fn, RFN, and the cross correlation function, because it's a measure of how a signal is correlated to another one, and because the noise is uncorrelated, then the SFN is zero. Okay, and thus your H1 of omega, that is the H1 estimator when we are having noise, okay, is simply the ratio between SFX of omega divided by SFF of omega. That is H of omega. So as we can see, when we are considering the H1 estimator, the noise is not affecting, the noise at the output stage is not affecting the estimate of your frequency response function. Okay, or in other words, the H1 estimator, okay, is unbiased. If noise is only at the output stage. Okay? And that comes straight from the definitions. Now, let's see what happens when we are having the output noise, but we are going to use the H2 estimator. Okay? So, let's consider if we are having H2. Go back to your notes and you can easily see that this H2 is given you by the ratio between the auto power spectral density of the output with respect to the cross power spectral density of the output and the input. So what we are having is S X X of omega divided by your S X F, but because we are having noise, we have to distinguish between the X and the measure X. So we have to consider XM, XM, because we are considering the measure quantity, as well as XM and then F. Okay, we can play the same, can use the same considerations as before. We can write that your XM, the auto power spectral density of the measure output measure quantity, could be viewed as the SXX of omega times your SN of omega, that is the auto power spectral density of the output and the auto power spectral density of the noise, compare to divided by SXF omega plus S and F for the same omega. For the same reason as before, noise is not correlated, okay, with whatever quantity, specifically with the input quantity. So we can move that. And what we got is that the H2 estimator is equal to your H, that is the actual frequency as a function, okay, times 1 plus S n omega divided by S x x omega, okay? And that is telling you that same system as before, but instead of using the H1 estimator, you are using the H2 estimator, then the result is that your FRF is not the one that you were expecting, because there is an additional term. Remember, the SNN of omega is the auto power spectral density of the noise. And if you consider all the omegas, then that is equal to the variance of the noise. Okay, so that term is a positive quantity. So we are having an FRF, an estimate of the FRF, an estimate of the frequency response function that is not the true one. It is different. So what we can say is that the H2 estimator is biased and overestimates your true H of omega, sorry, okay, if we have output noise. Okay, so please compare, before leaving these two effects of noise, H2 and H1. So we are having the same noise, that is, the noise is affecting the output stage, but if you are using the H1 estimator and the H2 estimator, the result is not the same. Okay, so noise is making the difference. The noise is not affecting the H1 estimator, whereas it's biasing, and specifically it overestimates the FRF when using the H2 estimator. Okay, time is over. Thank you for your attention. Do you have any questions? Okay, so if not, thank you very much. See you tomorrow. Okay, bye bye.